Welcome everyone to the Spectral Geometry in the Cloud seminar. Today we have the pleasure of having Maria del Mar Gonzalez, and she will speak about third-order eigenvalue problems. Stage is yours.
So thank you very much for the invitation, and it's a pleasure to give a talk here, and especially because this is a field a little bit outside my own, so I can always learn from others. Now, if you have any questions or something, or the sound is not clear or whatever, just please do ask me. And okay, so this is a handwritten talk. I made transparencies, handwritten transparencies, and let me start with the math. I'm going to talk about two papers that they've been recently published. The first one is with David Bosso, Carles Falcó, and Manuel Miranda. And the second one is joined with Maria. So let me start with the first paper. So this is more like an analysis paper. The second one is going to be more geometric, but they have I'm studying the type of objects. So what I would like to study is third order eigenvalue problems. And by third order, I mean they are boundary of third order boundary operators of fourth order operators in the bulk. So let me set up the problem. Let me take omega to be a boundary domain in a Rn with a smooth boundary. I'm not going to worry about the smoothness for now. And nu to be the outward normal vector. And let me consider the following energy functional. I integrate the bi-Laplacian energy in the bulk, so this is Laplacian u squared, and then I divide by both the L2 norm of u in domain plus a parameter gamma, the L2 norm of u on the boundary. So you see that there is a coupling between the bulk, the inside, and the boundary. I'm going to consider also the following function space. So h is going to be h2 functions, and I want them to have a normal derivative equal to 0. Now my parameter, it can be anything from 0 to infinity. You see if it's either 0 or at infinity, you decouple the bulk and the boundary. So now if you take the Euler-Lagrange equation for this energy functional, you see that in the domain, you have the operator L, that is just the bi-Laplacian. Now I'm going to consider only the first order boundary condition 0 Neumann. You'll see later that you can change this by other first order conditions. Let me stick to that. And the operator I'm going to be interested in is going to call B. It's going to be third order. And it is the normal derivative of the Laplacian of u on the boundary. Okay, with a minus. Now, the eigenvalue problem for this, you see that there is an eigenvalue in the bulk, an eigenvalue in the boundary with the parameter gamma. So you see that this eigenvalue problem has a coupling between the bulk and the boundary. Now, where does this come from, this operator? So some historical remarks. If you look at only at the eigenvalue problem on the boundary, this means to ask the parameter gamma to be infinity. I mean, you have to do some, you have to rewrite the function a little bit to make sense of this gamma equals to infinity. But essentially, it's like you only have the boundary term. This problem was studied by Carlo Ranzi Gilito in the 60s, and it's called a biharmonic Steklov eigenvalue problem. Now, for other gammas, for other values of the parameter gamma from 0 and infinity, my problem, I learned it because it appears in the linearization of the Canghilliard equation with dynamic boundary conditions. Now, this problem has been recently studied by, I put some names there, Nov, Signori, Nov, Lam, Liu, Metz, yeah. And okay, they study the nonlinear problem. They can clear the equation where they put a double well potential both in the inside and the boundary. When you linearize, you have both the eigenvalue in the bulk and on the boundary. So that's kind of the motivation to study this type of problems. Now, I'm not going to talk about this. And let me just give a quick review of the function analysis involved of this type of equation. So let me remember, inside we have a bilaplacian, and I'm looking at the problem with this third order operator. And okay, I always take zero Neumann. Just if I don't say, just remember it's there, because the fourth order operator needs two boundary conditions. So if I look at the solvability problem for this, I'm going to work with the L2 gamma space, in which the norm is given by an L2 norm inside and an L2 norm on the boundary. And then you can work a little bit, just use your favorite function analysis book, and you can give this as an exercise to your student, and you know that this problem given some f and g is solvable if and only if f and g satisfy a Fredholm or compatibility condition given by the integral of f gamma, the integral of g equals 0. But all of this is just a standard function analysis for this fourth order equation. Now, more importantly, is that a fourth order operator may not be self-adjoint, but here we are choosing the right boundary conditions so that the operator is self-adjoint in the classical sense. So then you know that it has good elliptic estimates, and then just you have a sequence of increasing, non-decreasing eigenvalues starting at 0. So all this is just kind of a standard, but think, okay, I have a nice operator, elliptic, and behaves well, so let me understand now the spectrum, or the first non-zero eigenvalue. Just as a first remark, let me look at the convergence to the limiting cases. And by limiting cases, when the parameter goes to 0, that this is when let me just go back up and look at the energy. And you see that in the energy, you have the bulk term. When gamma equals to 0, you only have the bulk term, and when gamma equals infinity, you only have the boundary term. For me, those are the limiting cases. Okay, so our first result is like when either you go to gamma equals to 0 or gamma to infinity, the theorem tells you that the eigenvalues converge properly, and also the eigenfunctions converge up to rescaling. Now, the proof of this, you use the monotonicity of in gamma and the min-max characterization of the eigenvalues. So I'm not going to stop here, and I'm going to go on the talk. Before, now we have a sequence of eigenvalues, and we would like to study, we would like to study these eigenvalues. So the first thing to do is to study model cases and if you use readily spherical harmonic decomposition, this is going to allow to calculate both the eigenvalues in the bulk case and in the anomalous case, and it will give you explicit formulas. So now for me, spherical harmonics, I can decompose a function that depends on r and theta, where r is positive and theta is just all the polar coordinates. And I'm going to write it as a superposition of spherical harmonics. Here I'm being very sloppy with the notation for the spherical harmonics. I'll try to be more careful later. But anyway, just remember that the spherical harmonics are the eigenfunctions of the Laplacian on the sphere in Sn-1. So now this is all quite standard. And just remember that the mode L equals to 0 corresponds to the radially symmetric eigenfunctions, and the mode L equals to 1, basically there is one eigenfunctions for each, one spherical harmonic for each coordinate. So anyway, now with this notation, we can solve explicitly the eigenvalue problem in the ball case. So now you know that the first eigenvalue is 0 because it corresponds to the constant. So I'm going to look only at the positive eigenvalues, and we see that the eigenvalues are those lambda. Okay, first project over spherical harmonics. So L is going to denote the Lth spherical harmonic projection. So for each of those projections, the eigenvalue is given by the solution of this equation. Now, all these are special functions, so let's just not worry too much about the specific shape. I will make a picture later. But in any case, now this is kind of a standard. Once you found your lambda, you can find your eigenfunctions explicitly also in terms of Bessel functions. Now, proof of this is just explicit calculation, and maybe a picture is more interesting. Now, if you plot, so the solutions of the lambda, all the solutions of this equation that I wrote, so that give you the lambda that are eigenfunctions, are the crossing of these colored lines with the black line. So you see that maybe expect that the first eigenvalue is the first eigenvalue is 0. Then you get a sequence of increasing eigenvalues, and what is interesting to observe here is that this point corresponds to the L equals 1 mode. So kind of the L equals to 1 mode seems to be the smallest one. And actually this is what the theorem is saying, is that the smallest non-zero eigenvalue corresponds to the mode L equals to 1. So this is quite close with what happens with the Laplacian, except that here the calculations are nastier. And the proof of this is just simple. If you use this as a test function in the energy, and you write it in terms, you do the calculation, you see that there is an L term here that is increasing with L. So the energy increases with L. And now you see that all the eigenvalues for the modes L greater than 1, they don't count, they're larger. And then for the 0 and 1 mode, you just compare it, and it's a simple calculation. But anyway, this gives you a nice characterization of the first non-zero eigenvalue. We go a little bit forward and look at the eigenvalue problem in the annulus. So now my annulus is going to be just all the points that have a modulus between A and 1. Now, you can do the spherical harmonic decomposition. You get again like a nasty formula with a lot of Bessel functions. But what happens here is that sometimes there is a bifurcation. So this is the picture for n equals to 2. And what happens is that there exists a critical size of the annulus such that for bigger annulus, the eigenfunction corresponding to the lowest non-zero eigenvalue is radially symmetric. So for big annulus, the eigenvalue, the smallest eigenvalue is radially symmetric. But for smallest annulus, the eigenfunction is not radially symmetric, but corresponds to the mode L equals to 1. And now this is what you can see here in the picture, that there is a region, like there is a bifurcation here, where on one side the smallest eigenvalue corresponds to the first mode, and on the other side the smallest eigenvalue corresponds to the radially symmetric solutions. So anyway, we'll see that this bifurcation, depending on the size of the annulus, is going to appear in the second part of the talk when I talk about geometric problems. But now what we would like to do is to work on optimization for this eigenvalue in so just in general domains, but that's something we're trying now. And we are getting to the second part of the talk, that is to look at eigenvalue problems in conformal geometry. Now, for the rest of the talk, I'm going to be working on 4 manifolds M, the Riemannian manifolds with a Riemannian metric G. So I'm going to restrict to dimension 4 because this is the critical dimension for a fourth order operator. The same way that the Laplacian behaves differently if you are working on a surface or on a higher dimensional manifold. So somehow 4 is the limiting case. Now, let me define the Panitch operator. I'm going to call it L, and it is a bilaplacian plus some geometric terms. Now the A is the Southern tensor, the J is the multiple of the scalar curvature. So we introduced this operator. It was introduced by Panitch in physics like long time ago, but it was it received a lot of attention by the group of Alice Chang and her collaborators, and I learned this in my thesis many years ago. Now here I'm giving the formulas only for manifolds. Now associated to the Panitch operator there is a Q curvature, because to all these type of operators that are conformally covariant or conformally invariant, I will explain in a moment what this means, there is an associated curvature. Or for instance, if you are working with the fractional Laplacian, then there is also an associated fractional curvatures. But let me stick to the Panitch operator, the fourth order Panitch operator. Now, the conformance invariance property, it means that if I change my metric conformally from G to G tilde, and by a conformal change, I mean that I multiply the metric by a positive function, that in this case, it is customary to write this function as e to the 2f, but it could be written, as long as it's positive, you can write it in many different places. Then there is a very simple law that relates the operator with respect to the metric G and with respect to the new metric G tilde. And indeed, oh, I think this is a 4, sorry. That should be -4. Sorry. So this is what I mean by conformal invariance. Also, the Q curvature of the new metric QG tilde can be related to the background Q curvature of the old metric by this semi-linear equation involving the Panitch operator. So this is a fourth order equation with an exponential nonlinearity. Again, this has received a lot of attention in PDEs and also for classification of 4 manifolds. Now, if M is a closed 4 manifold with no boundary, you have the Chern-Gauss-Bonnet formula, that it is the generalization to 4 manifolds of the usual Gauss-Bonnet formula. So this tells me that the Euler characteristic of the manifold times some multiple is given by this integral. Now, in this integral, there are 2 terms. The first one is the Weil, it's a Weil term. Now, the Weil tensor is, I'm not writing the formulas, but the Weil tensor is a conformal invariant. So if you are doing conformal geometry for manifolds, this term is not going to change, and what is going to characterize the geometry of the manifold is the Q curvature. And actually, the Q curvature is the important object in this business. For instance, let us restrict to locally conformally flat manifolds that I'm going to denote LCF. Locally conformally flat manifolds are manifolds that locally are conformally to Euclidean space, like for instance a sphere or a cylinder. If you are working with I like to work with locally conformally flat manifolds because they are the closest ones to surfaces on in dimension 2. But now in higher dimensions, one needs to look at locally conformally flat manifolds. And in this case, the Weil tensor is 0 and disappears, and actually the Q curvature is the one that controls the topology of the manifold. And this is going to be very useful for characterization and classification of four manifolds. Now, everything I've told you in these transparencies was for manifolds without boundary. Let me move now to what happens when my four manifold has a boundary. So now, let's look, when we have a boundary, I still have the Panitch operator L, is the Weil Laplacian plus blah, blah, blah. I wrote it before, but I need to add two boundary operators because it's a further order operator. So I take n of u to be the normal derivative of u, and b of u to be, I have the formula written down here. We'll look at it in a moment. But this b of u is the normal derivative of the Laplace of u with a minus sign. So if you compare this operator, this problem, to what I wrote in the first part of the talk, you see that what I was looking at in the first part of the talk was the flat case of the conformal version, because in the flat case all the curvatures disappear and you just get the pure operators. Now, okay, I have a bunch of lower order terms that they have some geometric meaning, and actually this is what it makes them interesting in conformal geometry. So let me just summarize. I'm going to work with four manifolds with boundary, in which I take the Weil Laplacian, okay, the Panitch operator inside, coupled with these two boundary operators. This first order boundary operator, I'm taking the simplest one. You could add like a term with mean curvature to make it look like an Escobar or Cherrier-Escobar problem, but let me not let me keep it simple. Just take the normal derivative of u, and then the new operator b that I'm interested in, the formula is written down here. You see the first order is the normal derivative of the Laplacian of u, and then it has many other terms depending on second fundamental form, mean curvature, etc. But for this talk, I will not need the full formula. Now, this type of operators appear first in some papers by Chang and Qing, and then all this theory was formalized in a paper by Jeffrey Case, and he has been doing a lot of advance in this direction. Now, the geometric interest of this operator, as I said, okay, take a four manifold with boundary that I'm going to call it sigma of dimension 3. Everything is smooth. I'm not worrying about the smoothness here. And the main property of this operator is the conformal invariance, as it happened with the Panitch. So again, if you change your metric from G to G tilde by a conformal factor, that I write it in this case as an exponential, I wrote down before the conformal law for the Panitch operator, but we observe, I mean, the important thing here is that the third order B operator is also conformally invariant, except that it has a different exponent. Now, so this coupling is what it makes it interesting to study these operators or manifolds with boundary. Now, you can give also a Chern-Gauss-Bonnet formula in dimension 4 for manifolds with boundary. And remember, look, you have the integral of the manifold, you have the Weil term, and the Q curvature term associated to L. But now, because you have a boundary, you have to add an integral of the boundary of these two terms. There is some part of the traceless second fundamental form that it vanishes if you ask that your boundary is umbilic, and just to simplify, I'm going to take an umbilic boundary in the talk, and then what it remains is this TG operator. Now, this TG operator is the curvature associated to my B operator the same way as the Q curvature is the curvature associated to the L operator. So somehow you see that, you see again the coupling. Now, the meaning of this Chern-Gauss-Bonnet formula, like, okay, what happens with surfaces? For surfaces, it's like the Euler characteristic of a surface with boundary. It has a Gauss curvature term that it's the inside the integral, but then you have also the integral of the geodesic curvature, because it is the geodesic curvature is the natural boundary object associated to the Gauss curvature. In four manifolds, it is the T curvature, it's the natural boundary curvature associated to the Q curvature. So I'm going, we wanted to study this coupling a little bit more closely and to understand what is the geometric meaning contained in the B operator or equivalently on the T curvature. And you see here, just let me rewrite again the curvature equation. So when you make a conformal change, you can relate the Q curvature Q tilde. I call it Q tilde, the curvature in the new conformal metric. It's related to the old one just by the L operator. And you see that there is a very similar formula. Oops, this missing tilde here. That you can relate the curvature in the old and in the new conformal metric just by an equation with the P operator very similar to the one with the L operator. So anyway, I hope I have done enough advertisement for these objects. Let me get to business. So now we would like to study some classification results using the Q curvature or the Q curvature. And just to simply, we started with the simple case that it's a locally conformally flat manifold in dimension 4 with umbilic boundary. Now, there is some recent paper by Alice Chang and I don't remember, with a collaborator, in which they try to work with classification results, but without the locally conformally flat hypothesis. But anyway, there is a lot of room to work here. Now, to start, let me just recall some easy results. If you start with a simply connected manifold with that has only one boundary component, then M is conformally equivalent to a half sphere. And actually, this is a simple topological argument, because your manifold, you can double it and then you get something close and connected. So there's nothing too deep there. Now, there is a paper by Rollo that we found. Actually, we proved this ourselves, and then we found his paper. So we said, okay, too bad. That if the Euler characteristic of the manifold is 1, and with positive Jamave constant, then your manifold is conformally equivalent to a half sphere. Now, our theorem in this direction is that if you start with a simply connected manifold but the boundary has two boundary components, then having both R, the scalar curvature positive, and the Q curvature positive implies that M is conformally equivalent to an annulus. Okay, I'll give you the proof in a second. Now just think that this rock, that an annulus is like when the R, the radial coordinate is between some rho and 1, this rho could be understood as the conformal modulus in higher dimensions. So now the proof of our result is basically like under the conditions of positive scalar curvature and positive Q curvature, the developing map is injective. Without boundary, this is a theorem of Chang, Hang, and Yang, and if you look at, so basically, you are able to map your manifold as a subdomain of the sphere, and it's injective. And if you look at their proof, you see, okay, what happens when you have a boundary, then there is you can generalize their work for when you have a boundary, and moreover, your boundary is mapped because of conformality. An umbilic map boundary has to be mapped to great circles on the sphere, and then just flatten it, and you get a flat annulus. And that's the proof. So now what do we want to do this? Because we would like to go back to the eigenvalue problem. I want to study the eigenvalues of third order boundary operators. So just quick review of the Steklov eigenvalue for surfaces. So now the Steklov eigenvalue problem is the following. Just solve for the Laplacian of u equals 0 on the boundary with Neumann when your eigenvalue mu comes in the Neumann condition of on the boundary of the equation. So now it is well known that there exists a non-increasing sequence of eigenvalues, and the first eigenvalue is 0 because you see it corresponds just to the constant functions. And we would like to understand the first non-zero eigenvalue that I'm going to call it mu1. Now, because of the variational characterization of the eigenvalues, you can write this as the infimum of an energy function that has the usual Dirichlet energy inside, divided by the integral of u squared on the boundary. And you have to, to kill the first eigenvalue, you have to make sure that the average of u is 0. So now this is well known, it was just a quick review. And I would like to study the first non-zero third order eigenvalue and to give some bounds for this eigenvalue. So now it is very classical that there are some topological bounds for the first Steklov eigenvalue. The first one is the classical result by Weinstock that basically tells you that mu1 is bounded by 2 pi, and you see that you need to understand, okay, to kill the rescaling, you have to multiply by the length of the boundary of omega. Now, if this is for domains in R2, then this result was generalized by Zhang and Yao, in which if you multiply mu1 by the length of the boundary, then you can bound it in terms of the genus and the number of n. So this is all very classical. Now you can also give geometric bounds, and actually, this is what we are going to get. In any case, so this was a quick review of the Steklov eigenvalue. Let me go to dimension 4 and look at the associated boundary eigenvalue. Remember, I have my L, my Panitch operator, just normal derivative equals to 0, and my third order operator, and I look at the eigenvalue problem associated to this third order operator. When M is a four manifold with boundary sigma, and again I have a sequence of eigenvalues, and the first eigenvalue is 0. So I would like to look at the next one, at lambda 1. So now you can write also a variational characterization for this problem in which you minimize overall functions with a zero average of the energy associated to this operator. Recall that, oh, this operator was a Biela plus. Okay, so this energy is going to be more the energy of the Biela plus all the curvature terms associated to the Panich operator, and you divide by the integral of u squared on the boundary. So this is kind of just a standard. You can give it as an exercise, and let's get to the bound. So this is our theorem. So remember, I'm looking at the first non-zero eigenvalue. So the first thing is that if M is conformally equivalent to a half sphere, then you have the following bound for the first eigenvalue. So you see that here I have to multiply by the volume, okay, not the volume, yeah, or the volume of the boundary, or the kind of the surface area of sigma. Now, this 24 pi squared comes because it is attained at the flat disk. So it's here this bound is sharp, and you can compare to what happens if you just have a flat disk. Now, here you get the interesting result. It's like if M is conformally equivalent to an annulus, then let's say I of rho, you can also give a bound that has the same type of scaling in terms of some constant that I'm not going to write down explicitly. And what it's interesting is that there exists some rho star such that if rho, which is the size of the annulus, is smaller than rho star, then this bound is sharp. But when rho is larger than this rho star, okay, at this rho star, bifurcation happens, and I will explain in a moment what this bifurcation is about. But you see, this is very similar to what happened with the annulus in the first part of the talk. I had a bifurcation depending on the size of the annulus. So let me give the proof of this result. Let me start with the case that M is conformally equivalent to a half sphere. So this means that I can map M to the unit ball before by this phi, and let me take phi M to be the coordinate functions. The usual Hertz calibration trick tells me that they integrate to zero, so actually they are going to be good test functions. But I'm going to take basically I'm going to take the eigenfunctions that I knew, the eigenfunctions corresponding to the L equals to 1 mode that I knew that they happen at the ball, and then I'm going to transplant them to the manifold by this phi operator. And you know how the eigenfunctions for the L equals to 1 mode are, because they can be written in terms of the spherical harmonics. Now, if you use this, so basically I'm using the L equals to 1 mode to test my Rayleigh quotient for the eigenvalue. So look, let's see what happens here. Because of the conformal invariance, I can write the energy on the manifold, I can relate it to the energy on the unit ball, on the ball model. And now I use the variational characterization just to say, okay, this is greater or equal than the whatever happens on the boundary times lambda 1. And you realize, oh, but these coordinate functions are to 1. So somehow all these guys are going to sum. When I sum on M, they are going to add up to 1, and the only thing it remains is the volume of sigma, and then the lambda 1. And now I didn't write down the number that comes on the right-hand side, but basically, because you are working on the ball model, you can calculate explicitly what happens in the ball model. So that's the end of the proof in the hash, if you are conformally equivalent to hash sphere. Yes, okay, map your manifold to a ball, use the eigenfunctions on the ball, and come back. That's not too difficult. Let me get to the part that I find more interesting, and actually this was the motivation for the developing of this whole line of research, like why I was interested initially in the problem, is that if M is when M is conformally equivalent to an annulus. So let me write the annulus. Okay, from R to 1. Now the inspiration is the series of works of Fraser-Schoen for the Steklov eigenvalue, because there they have a bifurcation result depending on the size of the annulus for the Steklov eigenvalue. And the same thing that it happens in their work is going to happen here for this third order eigenvalue problem. Now the proof, if you look at the proof, this one is going to be very similar. Like once you realize that you can do this for a third order operator, then okay, it may be a nasty calculation, but you can do it. So for us, what it was surprising is like we had this structure. So okay, so basically the first thing in the proof is that we use conformal invariance to translate our manifold M to the model that it's a flat annulus. And now when you have a flat annulus, you sit down and it's a heavy calculation, but you can write down all the eigenvalues and the eigenfunctions, kind of. We don't have a precise we don't have such a nice spectrum as you have for an annulus in dimension 2, but you can still do something. And what happens is like for the mode L equals to 0, then instead of just having the constant eigenfunction and the 0 eigenvalue, you have two eigenvalues that I'm going to call lambda 0 minus and lambda 0 plus. Lambda 0 minus is 0 and it corresponds to the constant eigenfunction, so we don't care about it. But there is this lambda 0 plus that I'm going to use as a test function in the Rayleigh quotient for the eigenvalue. Now, in the mode L equals to 1, then I also have two eigenvalues with two associated eigenfunctions that let me call them lambda 1 minus and lambda 1 plus. But in all this picture, the only important ones are these two here. The lambda 0 plus and the lambda 1 minus that are in competition. So basically, depending on the size of the annulus, one is smaller than the other. And this leads to a bifurcation. And I don't really, I mean, I could go into like the details of the proof, but I think you have seen the idea, and this the calculation of these eigenvalues and eigenfunctions is just a nasty calculation. And maybe I have been speaking for 45 minutes. I think it's a good time to stop. So thank you.
Thank you very much for the great talk. So we have time for questions. Don't hesitate to unmute yourself if you have a question.
Oh,
Lord says thank you.
Thank you to you. Thanks for coming.
I have a question, actually a very general question. Do you know if, I mean, in the work of Fraser and Schoen, there is a lot of other things to do with the links between Steklov eigenvalues and, I don't know, free boundary minimal surfaces and a lot of different things. Is there such a theory that is developed in this context as well?
We tried. We didn't get very far, but I think there is a kind of there should be a lot of work to do there. So we wrote this when in the COVID confinement, and then we didn't get back to it for some time. But I think there is a lot of room to work.
And so I was wondering, is there any other, so in dimension, say 2 or 3, I can imagine that has a half sphere and an annulus are kind of the two of the simplest shapes you want to look at. In dimension 4, is there any other simple tips which might be interesting to or feasible to look at?
We started with locally conformally flat manifolds with umbilic boundary. So our theorem tells you that if you are simply connected and you have two boundary components with positive curvature, then you are conformally equivalent to an annulus. So basically, if you are in the positive curvature assumption, then these are the two models that you are looking at. Now, leaving the world of locally conformally flat manifolds and umbilic boundary, I mean, this is the paper I mentioned by Alice Chang. It's a kind of recent one. I think there is a lot of room to work there, but it would involve looking at the whole Gauss-Bonnet formula, because with my assumptions, I killed two of the terms. And now you would need to work with the whole thing. But again, there is a lot of room. Just that we were, since we had this classification result, then we said, okay, our models are ball or annulus.
Yeah, to be fair. And so about this bifurcation, do you know that under a certain value, you only have one of the behaviors and over this value, the other one? Or do you know that you can change several times?
You mean depending on the size of the annulus?
Yes.
Yes, it's for, I don't remember now if it's for a small annulus or big annulus, but yes, it's one way or the other one.
Two behaviors and you switch from one to the other only once.
Yes.
Cool. Thank you very much. So, okay. So there's a question in the chat. Mohammed Al-Hadi asking, is it easy to apply the present results in, sorry, just close.
In higher dimensional manifolds? Okay. My answer is just theoretically yes. Practically, the thing is that, for instance, if you work with 6 manifolds, then you need to look at 6th order operators, so you need 3 boundary conditions, and there are not formulas for the, well, maybe Jeffrey Case is working on it. I think Jeffrey Case has the 3 conditions associated for a 6 manifold. So I don't remember now. So anyway, theoretically yes. Practically, it's very hard to get these formulas to make the operator conformal. If you only look at the flat case, yes, you can do many things.
Thank you for the question.
Thank you.
Did anyone else have a question? Well, in that case, we can thank Maria again for the great talk. We meet again next week with a talk by Michael Nahon, who will talk about the sharp stability of higher order Dirichlet eigenvalues. I wish you a very nice week to everyone.
So, hi, I just wanted to say hi to Mar. Hi, it's Clara.
Hi.
Do you see me?
No, wait, I lost the, oh, where, oh, hi.
Yeah, hi. So, yeah, I have not seen you for many years, so that's very nice work. Thanks for the talk.
Thank you.
Okay.
And maybe can I say hi to Samuel, that it's somewhere in the audience, and he has worked on the eigenvalue problem for the Punnett operator on manifolds without boundaries. So I'll make an advertisement of his work. Oh, but maybe he already left. Anyway, I made the advertisement.
Thank you very much. Well, have a nice.
Thank you for the great talk. Have a great